charmed, like I just summarized. The third contains the bottom and the top. Free quarks are not observed, however. They are always confined into composite particles called hadrons. So a hadron's example would be the proton or the neutron, for example. These particles include the baryons, which are combinations of three quarks, the most familiar examples of which are the proton and the neutron. So again, the baryons, like I was mentioning, is a composite of quarks. The most familiar ones are, of course, the protons and the neutrons, and these are the ones that we know and love. And pretty much in cosmology, that's what people mean. They mean the protons and neutrons generally when they mean baryons. There are many other hadron states, but most of them are very unstable. So you might make these hadron states, which are composites of quarks, but if they're super unstable and you never meet them in real life or in nature, then it might not be something that you want to deeply study. They might be produced in accelerator experiments, like the ones we've set up, for example, at the Large Hadron Collider, et cetera, or in the Big Bang, but do not hang around for long before decaying. So unfortunately, a lot of these more exotic particles, if you will, in the particle physics summary called the Standard Model of Particle Physics, include particles that they don't hang around for long. They decay within a short time. And so because they decay, we would not really see them too much, encounter them too much. Using our current understanding, it seems that within 1/1,000,000th of a second of the beginning of time, quarks have sufficient energy to tear themselves free. At earlier times than this, the familiar hadronic particles dissolve into a soup of quarks. Each of the fermions also has a mirror image version called its antiparticle. So you might remember we talked about like two, basically a pair at one point, and that's because all of these particles, all these fermions actually also have antiparticles. In a sense, never mind. I was going to say something else, but it's not important right now. But anyway, each of the fermions also has an antiparticle. It's sort of a mirror image particle, like a pair partner, basically. And this is an antiparticle. So this is not to be confused with the supersymmetry super partner particle that particles may also have, which is what the concept of supersymmetry theorizes. But this is antiparticle. This is well within the realms of Standard Model of Particle Physics. Okay, so for example, electron antiparticle is positron, and that's been seen. It's a thing. It's definitely possible in nature to have a positron. There are more processes that make electrons than do positrons. So we have more electrons generally than positrons. But antiparticles are nothing so bad, nothing too exotic or weird. Just a partner of these particles. Okay. The antiparticle of the electron is a positron. There are also anti-quarks and anti-neutrinos. So sometimes within a particle physics interaction reaction process thing, you might get out the particle or its antiparticle, but the flavor would be one of those flavors that we just talked about. Like it could be an electron, a muon, or a tau, or it could be an anti-electron, an anti-muon, or an anti-tau. Where if it's an anti-electron, we would just call it a positron, or it could be a neutrino that's involved somewhere in some process. But actually, when it does something, it becomes what comes out is an anti-neutrino. For example, you might see sometimes it's denoted with like a bar on top of the symbol, okay? The theory of QED describes interactions between the charged fermions. Right, so quantum electrodynamics, of course, we're talking about electrodynamics or electromagnetism with quantum mechanics included. So, of course, electromagnetism, it's important between charged particles, right? If there's not a charge, then there's no electromagnetism. There's no electromagnetic force. And so out of all the particles, whoever has charge, whichever ones have charge, are going to interact with the electromagnetic force. So it's going to be like you need to have QED or quantum electrodynamics for these particles that have charge because they have electromagnetism as well as quantum in their life, basically. Okay. So that